Fly me to the moon, let me play among the stars, and let me see what spring is like on Jupiter and Mars.
Hello everyone. So today we are going to be talking about Kepler's laws of planetary motion. Now Johann Kepler proposed these laws in the early 17th century, and although Isaac Newton later proved that the three laws proposed by Kepler were actually a result of his own, Kepler discovered them using only astronomical data, albeit in very large quantities. This was a very impressive feat, especially when considering that Kepler formulated these laws to model the motion of planets around the Sun, yet they apply equally well to all other orbiting bodies subject to gravitational force. However, Kepler himself is not the main focus of today. Instead, we'll get right to work and take a look at the three laws themselves. The first law is the law of ellipses, which simply states that the path of planets around the Sun is elliptical in shape, with the center of the Sun being one focus of the ellipse. Kepler's second law is the law of equal area, and it states that an imaginary line drawn from the center of the Sun to the center of a planet will sweep out equal amounts of area in equal intervals of time. Lastly, the third law, or the law of harmonies, states that the orbital period of a planet squared is directly proportional to the cube of the semi-major axis of its orbit. The rest of this video will focus on specifically outlining the proofs of the second and third law, as the first can be found on page 844 of Stewart's Calculus Early Transcendentals. To start, let's revisit the second law. Visually, this law states that the area a planet sweeps out in time t is equal anywhere along its path of motion. So given the same time interval, the area between points A and B will be the exact same as that between points B and C. To prove this, we must first familiarize ourselves with some notation. Namely, we must remember that we are using a coordinate system in which the Sun is at the origin, and the vector r, which is the position vector of the planet, is equal to r cosine theta in the I hat, or x direction, plus r sine theta in the j hat, or y direction. This means that r primed will equal the velocity vector, although we will save that for later. Lastly, u hat is the unit vector in the direction of r, meaning it is equal to cosine theta in the I hat direction and sine theta in the j hat direction. Visually, the notation we went over looks like this. The position vector r can be seen extending from the Sun at the origin, u hat is the unit vector in the r direction, and the velocity vector v, or r prime, is tangent to the r vector. Now when we cross the position vector r with the velocity vector v, we are given a vector perpendicular to both, as they both lie on the xy plane. This perpendicular vector is called vector h, and it extends into the z or k hat direction. Writing this out, we can see that the vector r cross the vector v is the same as the vector r cross the vector r prime, or more simply, the value of r in the u hat direction crossed with r in the u hat direction primed. If we then simply perform the product rule, rearrange, and simplify, we are left with r squared multiplied by u hat cross u hat prime. If we recall our definition of u hat in polar coordinates as cosine theta in the I hat direction and sine theta in the j hat direction, then the derivative of u hat, or u hat prime, must equal to negative sine theta in the I hat direction and cosine theta in the j hat direction by d theta over dt, as it is a partial derivative. Now, by performing the cross product on these two equations, we are left with r squared by d theta over dt in the k hat or z direction. And this makes sense, given that crossing two parallel vectors yields a perpendicular product. From the first law, we know that the magnitude of vector h is just h. This means that if we take the magnitude of r squared, d theta over dt in the k hat direction, we should be left with just r squared d theta over dt. This is exactly what we find. And this particular expression is very important, as we have shown that given any radius at a corresponding theta and time, we have a constant value, h. This will prove to be extremely beneficial in proving the second law. But let us first examine what the area swept out by a planet's path consists of. The total change of area between r at time t0 and r at time t1 can be thought of as a triangle at small enough intervals, meaning we can use an area formula in which the base is the change in position and the height is the radius. This gives us a formula of 1/2 multiplied by the magnitude of the position vector crossed with the change in position. From a basic understanding of motion, we know that the change in position, or distance traveled, is equal to the velocity vector by the change in time. Subbing this into our area formula, we are given 1/2 by the magnitude of the position vector crossed with the velocity vector multiplied by the change in time. And from earlier, we know that the vector r cross the vector v is simply the vector h. Rewriting this, because we know that the magnitude of the vector h is simply h, and h is equal to r squared d theta over dt, the area can be given by 1/2 r squared d theta over dt multiplied by the change in time. At small enough time intervals, the delta can be changed to a d, and by bringing the dt over, we are given dA over dt is equal to 1/2 r squared d theta over dt, more simply put, 1/2 h. This proves Kepler's second law, showing that the area swept out in a particular time interval is equal to a constant value, something that is quite incredible. All right, now let's move on to Kepler's third law, the law of harmonies. Remember that this particular law states that the orbital period of a planet squared is directly proportional to the semi-major axis of the orbit cubed. First, let's visualize the period and semi-major axis. The period, of course, is easy to see. It is simply the time it takes to orbit once around the entire ellipse. And the semi-major axis can be seen represented by A, where B is the semi-minor axis. We are going to prove this law in steps. So let's first remember that the area of an ellipse is given by pi AB, where A and B are the semi-major and minor axes, respectively. Let us also recall our proof of the second law, in which the change in area over a change in time is equal to 1/2 h. If we think about this for a minute, we can sub both the area of an ellipse and the period into this expression, because if we treat the change in area as the entire ellipse, the corresponding time is equivalent to the period, yielding the expression pi AB over the period being equal to 1/2 h. After some simple rearranging, we can then say that the period is equal to 2 pi AB over h. The next part of this proof relies on expressions found on page 663 of Stewart's Calculus, Early Transcendentals, and some simple algebra. Specifically, we will be using expressions which show that h squared over gm, the gravitational constant, is equal to b squared over a. Rearranging that, we get that b squared over h squared is equal to a over gm. If we look back to our earlier expression that the period is equal to 2 pi AB over h and square both sides, we are left with 4 pi squared by a squared b squared all over h squared. But now we have a b squared over an h squared, and we can sub in a over gm. This gives us t squared being equal to 4 pi squared a squared multiplied by a over gm. Simplifying this gives us an expression in which the period squared is equal to 4 pi squared by a cubed over gm. As 4 pi squared over gm will always be a constant, we have just proven the third law, that the period squared is directly proportional to the semi-major axis cubed. That's all for today. Thanks for watching, and I hope this video helped explain Kepler's laws of planetary motion.